If we can get through this next couple of examples, you'll have the rest of the class period to do 5.1, your homework, okay? And then tomorrow we'll start 5.2. Sound good? All right, so we have a particle moves in a straight line so that its acceleration at time t is given by this function a of t, okay? A lot of times you'll get the function for acceleration. Sometimes you just have to know that it's accelerating at 32 feet per second, which is where that was in the example. It says its initial velocity is v naught equals negative 6 centimeters per second. And its initial position is s of 0 is 9 centimeters. Find its position function, s of t. Okay, so this is not much different than the problem we did yesterday, where they started us at f double prime and they said find f. Okay, here we have f double prime, also known as acceleration. Find s, right? So our first move here is going to be to say that velocity is the antiderivative of acceleration. So if acceleration is 6t plus 4, then working backwards one step takes us to v of t equals what?
6t squared over 2 plus
6t squared over 2 plus 4t. He's absent today.
plus c.
Plus c. Plus c. Don't forget the plus c.
I did.
Okay.
That's why I'm not the...
That's why you're not the c monster? Okay, so when we simplify, we're going to have 3t squared plus 4t plus c. And we'd love to know what that c is. We have a way of finding it by knowing that v of 0 is negative 6. So if I can set my function equal to negative 6 when t equals 0, we get that c is negative 6. Okay, so a lot of times that is going to just zero out all of those terms and you're left with the constant being that initial value. But like we saw yesterday, it's worth it to plug in and make sure that that's what's going to happen. Okay, anytime I have e to the 0, that's not what's happening anymore. So my velocity function, v of t, is actually written as 3t squared plus 4t minus 6. Everybody okay with that? Yep. And then the last thing that we have to do here is find the position function, s of t. And we know that position is the antiderivative of velocity. Position is the antiderivative of velocity. So we're going to have 3 what? Plus 4t minus 6t plus d. And we can find that d term by setting position equal to 9 when t equals 0. Okay, so I skipped some steps here as far as simplifying are concerned. The 3's are going to cancel. Next, I'm going to have 2 times 0 squared because the 4 and the 2 made a 2t squared. Minus 6 times 0 plus d. So I can tell that d is 9. So my position function, finally, s of t, is going to equal t cubed plus 2t squared minus 6t plus 9. Okay. So I want to start this next page with that position function. S of t equals, what was it? T cubed plus 2t squared minus 6t plus 9. That's our position function. T cubed plus 2t squared minus 6t plus 9. What's acceleration? Find it. Prove it.
Together or
So let's go to velocity. What's my velocity function going to be?
3t squared plus 4t minus 6.
You see? So it works both ways. I like to check myself. After I've gone through anti-differentiation twice, I want to differentiate twice to make sure I got back to where I started. And make sure I didn't lose anything or lose any constants. Okay. Any questions on this one? Anybody? Okay. So I feel like this question is very straightforward as far as rectilinear motion is concerned. I feel like the next question has a lot more in-depth setup. So let us do it. This is example 7. It says, what goes up must come down. A ball is thrown upward with a velocity of 48 feet per second. Okay, so what are they giving me right there with that 48 feet per second? Okay, they're not giving me the velocity as a function. They're giving me an initial velocity. This would be, if I was writing it in physics, v naught. Okay, but instead, let's call it v of 0. V at time t equals 0. That's our 48 feet per second. Initial velocity. Okay. This is happening from the edge of a cliff that is 432 feet above the ground. There's our S of 0. S of 0 happens to be 432 feet above the ground. Velocities in feet per second. S of 0 is going to be feet. This is an upward velocity, so I've understood this 48 to be positive, which means that our acceleration would be negative. Since I'm in feet per second, that acceleration as it relates to time is going to be negative 32 feet per second. It's like in physics, we use an automatic 10 or an automatic 9.8. If you're in feet, it's an automatic 32. Okay. I didn't just pull that out of thin air. It is the number. On Earth. It doesn't have to be the number everywhere.
Second square,
Yeah. So find the ball's height above ground t seconds later. So we're going to have to do a whole lot of work to get to that. What's it asking? Find the ball's height above ground at t seconds. What is it looking for?
When velocity is equal to 0. Maximum height.
Is it?
It says when does the ball retract in height?
Right. So the first question, though, is find the ball's height above ground
Oh, I didn't see that one.
at t seconds. So what does that mean?
We need a function for position. Right?
For position. We need a function for position at any time t. It's not specific. So find the height above ground t seconds later. That's saying find S of t. Get a function for time or for position. Okay. In order to do that, we're going to start with our acceleration, which is this constant negative 32. So we go from there straight into a velocity function, which is the antiderivative of acceleration. So what's my velocity function? So negative 32t plus c. We can find that c by using our initial velocity component here that says v of 0 equals negative 32 times 0 plus c. And v of 0 here is 48. So 48 must equal c. So my velocity function is going to be negative 32t plus 48. Velocity function. Have you seen a formula that looked like this? That's how they got that. They did the calculus to get that formula. Okay. All right, so from here, what do? We need to find our position function. S of t is going to equal negative 32t squared over 2 plus 48t plus what? D. So S of t is going to be negative 16t squared plus 48t plus d. And how do we find d?
Substitute t.
Yeah, plug in that 0, and we know that, can we skip ahead to that? Can we know that d is 48? Okay. So d is 48.
No.
No lies. Okay. D is 432. I was like, that is a big old coinky-dink. So here's our S of t function, and I just want to throw this out here for just a second. Position is equal to x naught plus v naught times time plus half acceleration times time squared. Can you see all of the pieces? Can you see where they got this formula? Right? I mean, it's a direct derivation. Okay, I'll take all of those off now. Goodbye. Okay, so that's the first question. Find the ball's height t seconds later. This function would find the ball's height at any time t. Okay? The second question says, when does the ball reach its maximum height? When does the ball reach its maximum height? So how do we do that? Set the velocity equal to 0. We know that it's maxed out at the peak. So we set the velocity function, which is our v of t equals negative 32t plus 48. If we set that equal to 0 and solve for time, we will know when this ball hits its peak because the tangent line is equal to 0. Everybody following that here? Okay. Uh-huh. So that answers that question. The question was, when does the ball reach its max height? What's my question going to be for you at this point?
How tall is it?
What is the ball's max height? Right? So you're going to plug it into the position function. Plug what in? 1.5, because we know this is when it happens. Now I'm asking you, how high did it go in that amount of time? What is its max height? And our position function was that negative 16t squared. Given that it started at 432 meters or feet above the ground. Hmm? 468? So that tells me that the peak is not very far above the cliff that it was thrown. This is a pretty crude drawing, but the peak's not very high above the cliff where it was 432 to begin, and it peaked at 468. Pretty tall cliff. I don't think that the book asked you that question, but we should know. Okay, the last thing the ball wants to know is, or the question wants to know is, when does the ball hit the ground? So when, time-wise, does the ball land? When position is equal to 0. Okay, so when does the ball hit the ground? So that's when we set our S of t function equal to 0. Set your position equal to 0. So S of t is going to be that negative 16t squared plus 48t plus 432. How do we set that equal to 0? How do we solve? You could factor it. I don't think it factors. I don't want to try to do that.
We could move 432 over, and we could pull 16t from both of them.
Your options are factor or quadratic formula. That's a tendency that we all have. It doesn't work. That's a very sad route. You land in bad places. Why doesn't it work? I don't know. But it doesn't. This is sadness. We should use the quadratic formula here. Okay. Okay. So we're setting it equal to 0. We identify A, B, and C. Negative 48. Is he calculating? Are you calculating?
No, I'm looking at why it doesn't work.
Who is calculating? Do you have a number?
6.9.
T equals positive 6.9. 6.9 what? 0.8?
Yeah.
And then the other one?
Negative 35.
Negative 3.
908.
Thank you. Do we understand which one we should use?
Yes.
Based on my beautiful drawing? We know why the red one got thrown out. It's pre-time. Pre-thrown. It doesn't work. Okay? Time doesn't exist in the negative setting. And we're solving for time that it takes to hit the ground. How fast is it going when it hits the ground? Fast, she says. How do you find that? Say it louder. You use this time right here, and you go straight into your velocity function. Do the thing.
Negative 172. Oh, 6.
It's what?
Negative 173.06.
Faster or slower than it began? It did change directions. It became negative. It was thrown up positively.
Much faster.
It's much faster. Why?
Because it had 432 feet to get faster. To accelerate.
At what rate?
At a rate of 30 something? Was it
32. It's accelerating. It's going faster. And it changed direction, so now it's negative. Cool? You understand every inward and outward part of these kinds of problems? Good. Okay. A lot of your physics stuff will be over this kind of problem. And I think it's awesome that we've learned all of that, and now we can apply it back in this class. You can see how it works in calculus. Any questions at all on these two examples? No? I asked you more questions than they did in the textbook. Okay, but I feel like those are reasonable questions. I want to know, how fast is it going when it lands? That was the exact same kind of question that we asked about the kid on the diving board earlier. How fast is he going when he hits the water? You got to know when he hits the water. You got to know lots of different things there. So be prepared for any type of question that those might ask. I think that you have the rest of the class period today, which is about 15 minutes to work on that homework. That's what I would do. And then we'll start 5.2 tomorrow. Cool? Awesome.